Hi, I'm Larry Puckett, the DCC guy. You know, in a previous video I said that I was going to start remaking some of my older videos to bring them up to date. And the first one I'm going to be doing is on how to make your own Keep Alives. You know, I did a video on this a couple of years ago, and you know, it's done very well as far as the number of views go. So let's go ahead and get started. Okay, let's go ahead and get started with the remake of the video on building your own do-it-yourself stay-alive devices. Now, there is one thing that I do want to warn you about with these. This is a fairly simple circuit. You know, it's designed so that just about anybody can put these things together without sophisticated surface mount electronics and all of that kind of thing. Because of that, you know, there can be issues as far as down the road. If one of these capacitors in this series of capacitors starts to fail and starts to leak current, it could result in all of the others in sort of a domino effect failing as well. So that's one thing that can happen. And like anything electronics, it doesn't last potentially forever. But I suspect it's going to last a long time. I have not heard from anyone who has built any of these circuits having one fail on them. But a couple of people have mentioned in past comments that, you know, there is a potential for one to fail and then all of them in the series to fail. So just be aware of that. The other thing I wanted to point out is I will include a list of all these components that I'm mentioning as part of this video in the description to the video. So please, before you start writing me and asking me where you can get the capacitors, where you can get the diodes, all of that kind of stuff, look in the description, please. Read it. That's what it's there for. Also, I have done 4 other videos on Keep Alives, how to build them, how to design them, how to swap out components, how to redesign them, and how to make the connections. I will put a list of those various videos in a link right above me here, and also on the end screen at the end of the video. So one place or the other, you can find the videos that will tell you how this whole thing works, how it's designed, what all the components do, etc. So please take a few minutes to at least watch those if you have any questions about how to do this. So what I want to do now then is focus down here on the workbench, and we'll go ahead and start putting one of these together. Okay, here we are. I've got everything set up to go ahead and begin this project. Now first I'm going to go over the list of components. I'm using a 3-volt, 1 farad supercapacitor that I got from Mouser, and as I said, I will give you the information on where you can buy it and the stock number in the description. Okay, so I'm going to use 4 of those. They're rated at 3 volts, 1 farad each. So that's going to give me a total voltage of 12 volts. 3 fours are 12. Okay, that's enough to make this thing work. Now, the other components all came from All Electronics. I've got a 12 volt 1 watt Zener diode. I have a 1 amp rectifier diode. It's a standard old diode, 1N4001, I believe. And finally, I have a 1/2 watt 100 ohm resistor. And as I said, I explain in the videos what all of these do. So go ahead, watch the videos, and they'll tell you what you can what each one of these components is there for and what you can do if you need to swap them out. So I'm going to set those aside. That's all there is to this. It has a total of 4, 5, 6, 7 components and a few pieces of wire. Okay, so let's go ahead and get started. What I've done here is I've got these set up already on a double-sided piece of tape to hold them in place as I do the soldering. Now, as you can see here, hopefully, on the capacitor, there is a white stripe on one side. That is the negative side. Let me zoom in just a little bit more. Okay, there we go. Okay, so this white stripe indicates the negative leg, and that means the other side is positive. And if you look here, I've got these arranged negative, positive, negative, positive, negative, positive, negative, positive. So that's the straight setup. Now, what I'm going to do is I've got these set up so that I've pre-cut these wires, or the legs, so that they overlap here. And I'm just going to take my soldering iron and put a little bit of solder on each one like this. Okay. And finally over here. And that's all there is to getting the basic component built. So we now have 4 supercapacitors, 3 volts each, in series. That gives you a total of 12 volts. And that's why that Zener diode is a 12 volt Zener diode. We don't want these to be exposed to more than the 12 volts that they are rated at. Okay, so those are ready to go. Now, I already built up this component here. Let me show you it real close. Now what this is, it's just the diode and the resistor, and they're connected together. Notice that the white band on the diode is at this end. Okay, that has to be set up that way because these are polarized. Electricity will only flow in one direction with these. Okay, and I explained in the video, the other videos, why it's set up that way. And all you have to do is just, solder these together at each end. And I did this just to make it go faster. So I'm going to have this right here. Now the other component is the Zener diode. It's having trouble focusing on that because it's so small. But at any rate, that's a 12 volt Zener diode, and it acts as a voltage regulator. Now, I'm going to go ahead and connect these two together, right like this. Just bring them in here. It's kind of hard to do the soldering upside down here, but bear with me. Okay, there we go. Switch to my magnifying glasses here. Okay, so now you can see we have the Zener diode, and again, the black band is on this side. It's facing in this direction, same as this diode here. Okay, that's all there is to that one. Okay, now that we've got the these components all connected up, let's go ahead and attach them to our set of capacitors here. So the first thing we're going to want to do then is connect the Zener diode right here to the negative end of the series of capacitors, just like that. Pretty straightforward. Okay. Now, the next thing we want to do is, I've got this little green wire, and I'm going to run it between this point here on these guys. And I need to swap hands. This goes right here to the positive end. Okay, and all of these connections are shown in a diagram in the video I did on how these circuits work. Okay, so these are all shown in a diagram. So if you want to see a diagram of this circuit, go watch that video. Okay, now the final connection we have to make is the negative wire that's going to go to your decoder. For that, I'm going to use this black wire. And it gets attached here at the negative end of the series of capacitors. Okay? And I had previously attached the blue wire here. Okay? So the blue wire is your blue common on your decoder. And the black wire is the wire that goes to the negative ground contact on your decoder. And again, I explained that, how to find that, how to make the connection in the video I did on making the connection. So take a look at that video. Okay, so now we've got this all put together. All we need to do at this point is go ahead, slip it into this sleeve of heat shrink tubing. And I do this because it once this shrinks down, and you hit this with a heat gun, by the way, it's required in order to shrink these because it takes a significant temperature. I don't think a hair dryer set on high will work. I think you're going to have a regular heat gun made for heat shrink tubing or for stripping paint. Something like that is required. But at any rate, once you shrink that down, it's going to shrink down about 50%. And as you can see, it creates a nice tight package here. And that's going to prevent any of these solder connections from breaking loose. It's going to protect all of your wires that you just soldered together here and the components that you put on here. And it just protects the whole package, and it prevents any short circuits from occurring. So I think this is a necessary step, and I will include information on where I got that as well. It was either Amazon or eBay, I can't remember which, but there's just tons of it available on one of those sites. Now, let me point out that I built a number of these devices and used different components to test some things out. Now, this one right here is built using the 2.7 volt supercapacitors that you can get from Mouser. And with that one, that's 5 of them. That'll give you 13.5 volts. And then I built up this package using surface mount components. So it gives you a neater little package there. But about the only advantage to that is it's a little bit smaller and than working with something like this. And I think most people are going to find that they can work with these what are called through-hole components much easier than trying to deal with these little surface mount components. And that's why I've recommended using these as opposed to going the surface mount route. It's, the only advantage, the only thing you're going to get out of using these guys is maybe some eye strain because they are so difficult to work with, because they're so darn small. So this is the approach that I use, and it just saves you a lot of time in the long run, and it's easier to work with. Now, I also have tried different combinations, so let me point some of these out. This one here, as I said, is a 3 volt series here, so you've got 4 of them. That's 12 volts, just like the one I just showed you how to build. And this one here, as I said, is a 2.7 volt version, and that adds up to 13.5 volts. This one here is a different 2.7 volt version, but it's a bit smaller. These are only about a little over 6 millimeters in length. So as you can see, that gives you a slightly skinnier, maybe you can see it, let's see there, that gives you a slightly skinnier and not as tall package to work with. And in some situations that might be important to you. Now, but the real problem here is this particular supercapacitor is different in a certain way. And the difference is it has what's called an ESR rating of 1.8 ohms. Now, what is ESR? Now, it's something I haven't mentioned in the past, but basically it's an internal resistance. What I've been told by the electronics engineers is you should try to keep your ESR under 200 to 300 milliohms. This one here, these have a ESR, a resistance of about 1.8 ohms, so considerably higher than these here. Now, what does that mean in terms of how they work? Well, when I put this on a test motor setup, it will respond. You will get a small, you will get a current out of it, and it will keep the motor running. However, it will operate much slower than if I was using one of these circuits here, for example, with a much lower ESR of about 200 milliohms. So that's the big difference, but that's one thing you could try if you want. And that's one thing I didn't mention in the other video on how to swap these components out. For the most part, the ones that I have used in this one, and am recommending in this video and have recommended in previous videos are in that 200 milliohm range. So try to stick with that if you do go ahead and build some of these and swap out some of the components. Another thing that some people have asked me about these is, why do I need, 12 volts? Why do I need 15 volts? Whatever. Why, I just want the locomotive to get over dirty spots and dead spots. I don't need it to run 10 or 20 seconds. Well, the problem is decoders themselves, the mobile decoder portion of the circuit, needs 5 to 7 volts in order to operate. Even if it's not doing anything, it needs that in order to work. And the sound circuit needs 7 to 9 volts. So if you actually want your decoder to work, you're going to need something around 7 to 9 volts. And that's why you need these multiples of capacitors in order to get enough voltage to actually make the decoder work. It's not enough that you just want it to run for a few seconds or a second even. It has to be able to provide enough voltage to actually make the decoder itself operate. And that's what it comes down to. Okay? So you can't get around that. I've also heard from various people about what about some of the larger supercapacitors that I've seen advertised, 5 volts, higher values than that. Well, the fact is, once you get above this 3 volt size here, they start getting big fast as you go up in voltage. Some of these that are, say, 5 volts are going to be 20 millimeters across, almost an inch across. So, yes, you gain something from simplicity by using a smaller, by getting a higher voltage, but you lose something because they're bigger, and that's just the reality of it. I'm sure that in the future we're going to find that they are going to be able to find a way to redesign these and use different components in them that will give us much higher voltages for a much smaller device. But for now, this is what we have to work with. Now, if you do need something smaller, I did a video recently on TCS keep-alives when size matters, and they have found some very small capacitors that do a very good job with keep alive, and they work very well. They're much smaller devices. I have no idea where they're getting them or what they are or what the design is of the circuitry involved in them, but if you need a very small stay alive device, I suggest you take a look at the TCS KA1s and KA2s that I showed in that previous video. And I'll try to remember to put a link to that on the end page. Well, I hope that fills in some of the blanks you might have had about how to go about building these stay alive devices. They're not that hard to build. They don't take that many components, and they work. I mean, I've heard from a lot of people who keep telling me that they've built them themselves. So go ahead, give it a try, and let me know how it works for you.